In this problem, we're asked to find the pH of this salt solution. So the first thing we want to do is determine whether our salt, in this case barium hypochlorite, is acidic, basic, or neutral. So I want to start by doing what I've done here and go ahead and write out the equation for the dissociation of this salt. Now, to determine whether the salt is acidic, basic, or neutral, I consider the cation and the anion independently. So a cation can either be acidic or neutral. In the case of a metal cation, I need to consider its hydroxide. In this case, that's going to be barium hydroxide. All right, and then I need to ask, is barium hydroxide a strong base or a weak base? Barium hydroxide is one of the 8 strong bases that we need to know. So if this is a strong base, then that means that its counter ion, in this case barium 2+, is neutral. In the case of the anion, it can either be basic or neutral, and so I need to consider its conjugate acid. The conjugate acid of ClO- is HClO. This is not one of the 7 strong acids, so it's going to be a weak acid. So that means the conjugate base, ClO- is a weak base. So essentially what this problem is asking is, what is the pH of this basic ClO- solution? Now, we do have to be a little bit careful. We're told that the pH of our barium hypochlorite is 0.25 molar. But if we look at our equation, for every 1 mole of barium hypochlorite that dissociates, we form 2 moles of hypochlorite ions. So that means that the concentration of hypochlorite is going to be twice the concentration of the barium hypochlorite, or the initial concentration of ClO- is 0.50 molar. So that's what we'll use for the initial concentration of ClO- in our ice table that we'll build on the next slide. Alright, so I've already written out the equation. If we're thinking about ClO- acting like a base, the equation is the base plus water forms the conjugate acid plus hydroxide. If I want to know the pH of the solution, if I can determine the concentration of the hydroxide ions, then it's easy to determine the pH from that point. So if I go and fill in my ice table, we said on the previous slide that the initial concentration of ClO- is 0.5 molar. Water is a liquid, so I don't have to worry about it. Initial concentrations of HClO and hydroxide are 0. We'll call the change in ClO- minus X. That'll make these plus X. So at equilibrium, I'm going to have 0.5 minus X, X, and X. Alright, so I need to plug this into my equilibrium constant expression. In this case, Kb is equal to HClO times OH minus over ClO-. Now, we need the Kb for ClO-. This is probably not given in the textbook. What is given is the Ka of its conjugate acid. And we know that Kas of a conjugate acid, conjugate base pair are related. And they're related by the fact that the Ka of HClO times the Kb of ClO- is equal to Kw. So if I look at the table of acid dissociation constants in the textbook, I'll see that Ka of HClO is 2.9 times 10 to the minus 8. So if I use my relationship, that means that the Kb of ClO- is Kw divided by the Ka of HClO. So Ka is 1 times 10 to the minus 14 divided by 2.9 times 10 to the minus 8. And I get my Kb for ClO- is 3.5 times 10 to the minus 7. So in my equilibrium constant expression, I'll plug in this for Kb. I'll plug in my equilibrium row of my ice table, and I'll do that on the next slide. So I have my Kb. It's going to be equal to x squared over 0.5 minus x. Now in this case, the equilibrium constant is very small, so it's only going to go a little bit towards the products, and this minus x is going to be relatively small, so I can make the x a small simplifying assumption, so I don't have to worry about that. To solve the problem, I multiply both sides by a half, so I get 1.75 times 10 to the minus 7 is equal to x squared. I take the square root of both sides, and I find out that my x is 4.2 times 10 to the minus 4. And from the previous slide on our ice table, this is equal to the hydroxide ion concentration. So once I know the hydroxide ion concentration, finding the pH is pretty straightforward. We can do it a number of different ways. I'm going to find the pOH first. So pOH is minus the log of the hydroxide ion concentration. So in this case, I take the negative log of 4.2 times 10 to the minus 4, and I get a pOH of 3.38. Then I'll use that pH plus pOH is equal to 14. So in this case, my pH is 14 minus the pOH, or 14 minus 3.38, and so my pH is 10.62. And that's the answer to the problem.